time now for hands-on Arduino. Hands-on Arduino Part 5B, at long last. I've grown a little bit of hair since the last time I made one of these videos. Well, in our video today, we're going to be talking about Arduino to Arduino connection using SPI. That's the subject of our discussion today. The SPI connection, basically we have a master and we have a slave. We're going to have two Arduinos playing each of these roles. The master uses these four signals: the clock, the master out, slave in, master in, slave out, and slave select. Slave select bar means that it's active low, which means you pull it low in order to select. We connect to another Arduino these exact same four pins. So we just connect them pin for pin to each other, and that's the connection that we need. Here is an example of timing diagrams used in an SPI communication. So we have a number of steps that are taking place. Step A is what happens prior to transmission. Prior to transmission, the slave select pin is held high. So notice here are the pin numbers that we use: master out, slave in, master in, slave out, clock, slave select. So here, before we actually do any transmission, slave select is held high. When we want to start communication, the first thing that happens is we need to enable the slave and select it. So by pulling the slave select line low, we enable the slave. The slave then sets itself up to do the communications that are needed. And now, in this particular example, 3 bytes are going to be transmitted. In this case, they are the letters F, A, and B. And so what happens then is that the master establishes the clock and begins when the character F is put into the SPI data register. So this is actually the set of bits 0, 1, 0, 0, 0, 1, 1, 0. When that is put into the SPI data register, then the transmission begins. And so the clock counts off for 8 bits. And so these are actually those bits. So notice the first bit is 0, then a 1, then 3 zeros. It's hard to see that, but that's actually the length of 3 zeros. Then 2 ones, so that's the length of 2 ones, and then a 0. And then the clock ceases. And so when all 8 of those bits are transmitted, then the interrupt flag is set, indicating that a transmission is complete. The next byte is set. In this case, it's the letter A. And so the letter A, if you were to look at the bits, that you would see it is 0, then 1, 1, then all zeros, and then a 1. And that would be the letter A in binary. And then the letter B is transmitted next. And so you can see how it's set up. When a character or a byte is put into the SPI data register, as soon as possible afterwards, that is the next clock cycle, it begins transmitting. Okay. And we can set the transmission rate by adjusting the clock rate. So we can see all 3 bytes are transmitted, and then after that there's no more data, and then finally the slave is released. So this is an example of communicating, sending 3 bytes out. So you notice that from time 0, from the time the transmission, from the time this is pulled low until the end of the last byte is transmitted, the it takes 9 microseconds. So that's about 3 microseconds for each byte. So 3 bytes, 9 microseconds. Okay. So each clock cycle that we saw here takes about 1/4 of a microsecond, that is at 4 megahertz. It is theoretically possible to transmit faster, but there are many devices that do not support this. In terms of the slave select, each slave device has its own slave select pin. When the slave select is high, each slave should have its other connections in a high impedance state. Okay, that's the way they should be set up. A lot of this is done automatically by the SPI libraries in the Arduino, so we don't actually have to think about putting it into a high impedance state. A slave's master in slave out line should be configured to be an output. Okay, so if master in slave out, right? So slave out should be configured to be an output, if and only if the slave select line is taken low. In other words, the only time you do this is when the slave is actually selected. Otherwise, you might be competing with another slave. One slave may be competing with another slave in trying to communicate when it's not its turn. Okay, so a slave can only communicate when it's its turn, and it is its turn when its slave select line is taken low. So that's important to consider. In general, the SPI standard does not specify a protocol for how the communication takes place. What that means then is that the master and slave need to have some kind of agreement on what the data means. Is it string data? Is it numeric data? You know, what is it? And how many data values am I expecting to send? And all that kind of thing. So this is an important consideration, which means, first of all, it gives you a great deal of flexibility as to how you want the data to be transmitted. So I don't have to send all these start bits and stop bits, and I mean start and stop, and you know, I can do whatever I want, and that's great. It does require a little forethought, though, in terms of how are we going to actually do the communications. So it's important that data may be sent and received simultaneously. That is, the data is transmission is said to be full duplex. So that's pretty cool. And in general, a master might not even know if a slave is connected. So it's important to, in terms of synchronization, communication, it may be helpful, for example, in certain situations, for the master to just send out like a query to see whether or not the slave is even connected. And if the slave is connected, then that query can also communicate to the slave that it's ready, the master is ready to start sending and receiving data. Okay, so that's important. Now, in terms of the slave, the Arduino wants to be the master, but it can be used as a slave. As a slave, the transmission is interrupt driven. Okay, and when the transfer of a byte is complete, the interrupt service routine with this vector name, SPI STC, that is transmit complete, is really what that is. SPI transmit complete, but it seems kind of weird that would be SPI since there's already an SPI there. But anyway, I didn't make that name. All right, anyway, this is the interrupt vector, or the interrupt service routine name that needs to be defined. Okay, so the byte that is transmitted is put into the SPDR, SPI data register. Okay, the incoming data then may be collected into a buffer, for example, if you're sending a string of data. Okay, and a flag is set when a significant byte is received. So that is, communicates that a new line is received. So that's important if you're using string data. Not necessarily so important if you're working with numeric data. So this is the SPI as a slave. This brings us to our first example. The first example, we're going to be looking at SPI, and we're going to do a Hello World program. Thanks to Nick Gammon, who that awesome Australian, who posted this this awesome page on SPI communication. So there's a number of examples on this page, and so I recommend you go look at it. I didn't make all this stuff up myself. It is helpful to have good resources to draw upon, and there are lots of good resources. So this is the first example we're going to look at. And so basically we have two Arduinos connected to one another, and again we have the 4 lines connected to each other, and then we have a ground connected to each other. Okay, so you need to have that 5th line, a ground, on the communication. Now, what I'm going to be using is the Cat6 cable that I showed in the last lecture, and the Cat6 cable has 4 twisted pairs. Okay, so as you can see, I have 4 data, and then the twisted pairs means it has 4. The pairs are the data line and a ground. So basically, there are actually 8 wires in there in that cable, in a Cat6 cable, plus what's called a shield drain wire. Okay, the shield drain wire. So those grounds all need to be connected between these two. Okay, each of the grounds, and the shield drain wire also needs to be connected to a ground. Okay, so on one side we have, even though it looks like a single wire here, we actually have 5 wires connecting into that ground. And on this side we have 4 wires connected on the ground. That is, you only connect the drain wire up to one side. You don't connect it to both sides. Okay, otherwise you can create what's called a ground loop, and that's not a good plan. Okay, so anyway, so that's the plan. You connect all the ground wires up, and then you have the 4 data wires. And so these are the colors actually in the Cat5 cable that I use. So that's what the colors stand for. And notice I'm connected up to these 4 connections. Okay. Now I'm going to use the Nick Gammon's program here, except I'm going to modify it a little bit. So instead of just transmitting hello world, I'm going to alternate between transmitting hello world and bye bye world, and again doing that using SPI. So let's look at the code. So there are a number of parts of this code. The first part is the initial part, so I'm going to include the SPI library, and the SPI library does a number of significant things for us that we don't have to think about, which is helpful. I want to actually get in and actually show what registers need to be set and all that kind of stuff, and which actually is not that bad. But anyway, I'm going to use the SPI toolbox or library for now, and then I'm going to have this switch. So int switch SWI is a switch. Yeah, I know sometimes the variable names are cryptic, but anyway, so it's going to start off being 0. It's going to switch between 0 and 1. When it's 0, it's going to transmit the hello world. When it's 1, it's going to transmit the bye bye world. So here's the setup program. We first set the digital write high. The slave select high. So that is, we're not communicating. So we want it clear that we're not starting communications yet. Okay. Then we do an SPI begin, and what that does is it actually does a number of things. One of the things it does is it sets the data directions for your MOSI, the master out slave in, master in slave out. It sets the directions for those up properly. Okay, and it also so it sets all that up. It also, and then we have this command, SPI set clock divider. This adjusts the clock speed for the SPI communication. In this case, we're going to divide by 8. Okay, so that's what happens in the setup routine. Okay, in the loop routine, we have a number of things. We're going to be working with character strings. So the hello world is a character. Okay, so we're going to define C as a character. So that is actually the character that gets set. We're going to be sending one character at a time, and that is the character that gets sent as it gets sent. So we need that as a variable. Enable slave select. So now we're going to start the communication. So the first thing we do is we pull that slave select line low. Okay. Next we have, we alternate strings. So if the switch is 0, then we're going to do one thing. Otherwise, we're going to do this other thing. Okay. So in this case, we're going to be sending hello world with a carriage return, and that carriage return actually communicates to the software on the other end that we have sent the full string. Okay. So that carriage return at the end, that new line, basically communicates that we're done communicating our string. Okay, so notice this is a very unusual command. So let's kind of talk through it a little bit. Constant character *p. Okay, so what this is doing is it's setting up a character array, and these are the values in that character array. Okay, so it's going to start constant character, so it's *p is the address. And notice we're incrementing the address. And so what this is doing now is it's taking the first character at that address, and it's going through and it's going to do a loop of that. So notice that this is a for loop, and this is the only thing that's being done in that for loop. So I don't need curly braces because this is all like one line in a sense. And so what is this saying? Transfer that character. And so it's going character by character, doing the transfer. When it gets to the return, the new line, it's going to stop that transfer. Okay, so when switch is equal to 0, it's going to transmit hello world. When the switch is not 0, it's going to transmit bye bye world. Okay, character by character. And notice here I have a space between the P, the star, and the P. Here I don't have a space. Here I do have a space. It turns out C is kind of sloppy that way. It allows it to do either. But sometimes you'll see it one way, sometimes you'll see it another way. And then once we've done that transmission, then we shut down our SPI communication. So what's going to happen then is in our loop program, we're going to, the first time through the loop, switch is going to be 0. And so it's going to do this. Okay, shut down the communication. Then it's going to change the switch. So switch was 0, now it's going to be 1. And so the next time through the loop, it's going to be this. It's going to hit this instead of that. And so it's going to alternate between the two. And there's a 1-second delay that is set up in this whole thing to delay the communication, so that you can actually have time to read what's going on. Okay, so each time we're transmitting a different phrase, and so I chose to do it this way primarily so you can see it. There's, you know, I took the code, and I don't know about you, but whenever I'm given sample code, I always like to tweak it a little bit to make sure I understand exactly what the code is doing. And so this was just helpful for me to see what the code was doing. So I recommend that you try tweaking things. Make sure you save the copy that works, okay, and then tweak it and see what happens when you do that tweaking. So this is the master code. Let's move on to the slave code. In the slave code, again, I include the header. I have this buffer, okay, because in the master program, I didn't need a buffer array because by defining that character string within the for loop, I didn't actually have to create an array explicitly like this. So, but now I'm going to be receiving data, and I don't know how many data values I'm going to be receiving exactly, but in this program I can receive up to 100 values. Okay, I'm not expecting to receive more than that. Okay, and actually, since I know pretty much what I'm going to be sending and receiving, I could even change this number, but again, it's not necessary. So this is just sets it aside so that I can receive as many characters as I'm expecting to be transmitted. Okay, so again, that's part of this forethought in terms of how am I going to format the data that is being sent. And so in this case, all I know is that the data is going to be less than 100 or 100 or less string characters. Okay, string characters. In this particular case, I have these two volatile variables. So remember what a volatile variable is. It's a variable that can go in and out of interrupt service routines. Okay, so that's what the volatile is for. So byte pos is that's the position in the array, and the Boolean process it is saying, am I going to process it or not? Okay, am I going to process? Am I going to, when I'm done collecting a full string, a full message, hello world or bye bye world, when I'm done, this Boolean is going to be set, saying it's now time to do something with that data. Okay, in other words, before then, I don't want to do anything with the data because it's not all there yet. Okay, I don't want to do anything until I'm all done. So we start up the serial monitor. Okay, and notice I have as high of rate as possible. This whole communication goes really fast, and so even though this seems like it's really fast compared to 9600, which is the standard, it's not that bad. So then the Arduino wants to be a master, and so we could do SPI begin for the master, and that does a lot of the setup stuff. Well, it doesn't do it for a slave, so we have to kind of do things more manually for ourselves as a slave. So the first thing we need to do is set the MISO as an output. We need to set the SPI into slave mode, and so this is the command we need to do in order to set it as a slave mode. So this basically leaves that register SPI control register alone except for the bit at SPE. Okay, so SPI enable. Okay, by setting it, I'm putting it into slave mode. And then we're getting ready for an interrupt. So we're starting in our buffer at position 0, and we don't want to be processing the data yet, so this is false. And then we turn on the interrupts. SPI attach interrupts is actually used for the slave. We don't actually use this command in the master. So this tells us now I can attach an interrupt. And the interrupt we saw what the vector needed to be, right? The SPI STC vect, right? We had that we needed to use. Okay, so here is that interrupt service routine. Okay, interrupt service routine SPI STC vect. So this is the transfer complete. This is what happens when the transfer is complete. So I'm going to set into C the byte that's obtained in SPDR, SPI data register. So it's going to grab that byte, put it into C, and now we're going to take this and we're going to basically put it into the buffer at position pos, and then we're going to increment pos. Okay, so we're going to increment. So basically what this is going to do is it's going to put C into buffer position, and then it's going to increment the buffer position as long as the buffer position is less than the overall size of the buffer. Okay, in this case it's 100. Okay, and so we're also going to check if that character C is the new line. Then we're going to say we're done. Okay, so this is not done automatically. We have to actually check. So the fact that we have a \n here communicates that this is something that we have set up to indicate we're done with the communication transmission. We could have used any character or symbol here that we wanted to do that. Here we chose the new line to do that. It's kind of a natural, so it's reasonable to do that. And so this sets the Boolean value process it to be true. Okay, and so we do this. We'll do all of this as long as our buffer is not full. If our buffer is full, then we'll skip this. Okay, and so that's the interrupt service routine. And then we have our loop program. And so we only do this if a complete transmission occurs. So notice that in the loop, the only thing in here is this if statement. And so if process it is true, then we'll do this. Otherwise, we won't do it. It'll just sit here and wait. It's waiting for transmission. Okay, so first, the buffer position is 0, and it's going to print the buffer. Then it's going to reset. It's going to reset the position and also reset that bit. Okay, so here we're going to this is going to allow us to print out or display on the console, the serial monitor, what was in the buffer. So what's going to happen now is in this program, we're going to have we load each of these codes into their separate processor. In this case, we're going to leave the USB connector connected to the slave, okay, because we want to be able to have the serial monitor connected up to that slave. Okay, so we need that slave to be connected to our computer using the serial monitor, so we can actually read the console. And then we'll have the master just be on a 9-volt power supply. Okay, so this is the first example. Here we have the master program. Here's the slave program, and we have it running, and you can see that it is alternating between hello world and bye-bye world. So it is in fact working. Cool. Now we're going to move on to our second example. In our second example, we're working with SPI communications, and we're going to be doing simultaneous bidirectional communication. So we've talked a little bit about that. Now we're actually going to do it. Again, Arduino to Arduino. So first of all, we have that the SPI is designed to be full duplex. That means it's designed to transmit and receive simultaneously. So in terms of bidirectional, that's not a problem. In terms of simultaneous, that's not a problem. It's designed that way. So when the slave puts something onto its SPI data register, then the slave is ready to transmit. It cannot transmit, however. The transmission to the master will not occur until the master pulls the slave select low and the clock starts pulsing. So remember, until the slave select line is pulled low, the master in slave out line is actually in high Z state. Okay. So, but once the slave select low is pulled low, then the master in slave out MISO is set to be an output from the slave. And when the clock starts pulsing, then the data is transmitting. So when the clock pulses, data can actually be traveling in both directions, from the master and to the master. Now, the SPDR in both cases, in both slave and master, is what is called double buffered. Okay, and at first it's a little confusing what that means, and when I read it in the literature, it was not at all clear what it was saying. But what it's basically saying is that it has what's called a receive buffer as well as a transmit buffer. That is, this same register has two different buffers. It has a buffer for transmit and a buffer for receive. Okay, and so the master can put something onto its SPDR. Okay, and when it starts transmitting that, it has a receive buffer that's receiving data. So remember, you have a master in, slave out, master out, slave in. Those two are separate lines, so the data is not getting confused. Those lines are doing their bits, but one is going one direction, the other is going the other direction, and there is a buffer that's receiving that data in the same way there's a buffer that's sending that data. Okay, and they're both connected with this SPDR, and that's true both from the master side and from the slave side. Okay, they both have these, so So that's how, at first it seems confusing. How can the same register be transmitting and receiving at the same time? Doesn't the data just kind of like get, collision? No, it doesn't get a collision, and that's because there are separate actual buffers that work with that data, one to transmit and one to receive. Okay, so that's the concept of double buffer. So what happens is when the master puts that data onto its SPDR, or when the slave puts it into its SPDR, then when the transmission begins, that data is moved onto a buffer. Okay, that data is moved onto a buffer. It's no longer in that register. Also, there is the receive buffer set of buffers. Okay, and so as the data is coming in, it's going into that buffer. When the full set is in there, that data is moved into the register, SPDR. Okay, so that SPDR actually has bidirectional data. It has data on the way out and the data on the way in, which means you better, if you're sending and receiving data, you're going to put, for example, the master will put data on the SPDR, the data will go out, and then in the meantime, data will be coming in, and you need to read that register of the data before you put new data out on that register. Okay, so it's important, otherwise you just lose that data, right? So you need to make sure that you are reading and before you try to write new data. So that's the trick, okay? SPI communication is that concept of a double buffer on that register. Now, some synchronization may be required for our communication. That is, for example, the two Arduinos have programs, and those programs do not necessarily start at the same time, right? So for example, in our setup, we're only using one USB cable. We plug one USB cable in, we upload the code to one Arduino, then we remove the USB, upload the other code to the other Arduino, and then we can start, okay? And so the programs don't necessarily start at the same time, which may or may not be a problem, okay? If synchronization is required between the two, then the master needs to send some kind of a code byte to indicate that it's time to start. And so, for example, the slave would not try putting any data onto its SPDR before it receives that byte. And there may be a bunch of bytes that come until finally that one byte comes. Once that one byte comes, then it knows, okay, now it's time for me to start sending data. Okay, so that synchronization may be required. In some applications, synchronization is not required. For example, we're gonna do one using hardware that does not require that. So we'll come to that. So bidirectional communication. So here's our master code for this program, and so this is a takeoff of the previous program that we used. So this is my code. So again, we're including SPI. We're gonna notice in our master code, we're now going to use our serial. That should be orange. Serial. And then we're going to again set the slave select high. We're going to begin our SPI, and we're going to set our clock again at 8 by 8 divider. So that's our setup program. Very similar to what we had before, except we're doing serial begin. In our loop program, okay, in our loop program, we're going to define as a byte the two values, master value sent and master value received. So a sent and received values, okay? And each of those are going to be 1 byte. So we first set the digital write to be low. Okay, I'm sorry, the slave select, we're going to pull that low. And notice that we're not going to let it go high again until we've done all of this stuff. In other words, I know I'm going to be transmitting all this data, and then I'm going to pull the slave select high. So pulling it low and letting it go back high, it can be as long as you want in between there. Okay, so I pulled it low, and now I can send data. So notice that I'm basically cycling through from 0 to 255 values. Okay, and so the loop is going to go through those, and each time it's going to go through 0 to 255. So it's going to repeat sending 0 to 255. Okay, so that's the value sent is JJ. Okay, the value received. No, so where do we get the value received? Notice value received is equal to SPI transfer value sent. I was like, whoa, what's the deal with that? Okay, so what happens is this value gets put into the transmit buffer. What comes from the receive buffer gets put into this variable. Okay, so this one command does both the sending and receiving. Kind of tricky. Watch it. Okay, and then I have these serial print commands that are going to display onto the monitor what happened. It's going to display the sent value and the received value. Okay, and so this is going to happen. It's going to cycle through that, and then in between it's going to pause a second, and then it's going to start it over again. Okay, so that's the master code. The slave code is similar to what we had before. Again, we set MISO to be an output. We set SPE in our SPI control register. We do the process it thing again. We set that to be false, and then we attach our interrupts. So that's pretty much the same setup routine as we had before. For our interrupt service routine, notice I have just these two values. I'm going to put the received value into sval received. So this is the slave value received. Okay, slave value received, slave value sent. Okay, that's just to help me remember which I'm working with the master, I'm working with the slave. Okay, because remember the master value sent is the slave value received, and vice versa. So again, in our loop program, we're just doing we do nothing unless I received a byte. If I received a byte, then I do all this stuff. I put JJ into S value sent. Okay. So what is JJ? JJ is a counter. So it's an independent counter. Okay. And so I'm going to put that value into value sent, and I'm going to put that into SPDR. Okay. So that's the data. That's the data that's going to be transmitted. Then I'm going to increment JJ. And if JJ is greater than 254, I'm going to reset JJ. And then I'm going to reset process it. Okay, so this is what's happening. So basically, I'm bidirectionally sending values that increment. Okay, and so depending on when the programs start, one may increment before the other. But this is just to show that I can send and receive data at the same time. So all this is doing, this is not doing anything with the value that's sent. Okay, so in fact, I'm not even I'm nowhere in here. I'm receiving the value here, but I'm not doing anything with that value that's received. Okay, I'm not doing anything with it. Okay, I am sending it another value though. So I could do something with it. I could use it to control something or whatever. This is just to display the fact that I can send and receive data. And you'll have to take my word for it that this actually works. Okay. All right, so that's the slave code. So this is our second example. Here we have running the two programs, the master and the slave. The slave was loaded first, and then of course I use a 9-volt power supply to drive it. Then the master is run, and notice that when we started up the master, these two numbers are not synchronized. Okay, it's not synchronized because the slave was already running and was incrementing before the master had a chance to even start, and so you have that kind of situation that arises. So, and when we synchronize, I'm going to go ahead and push the reset buttons for both at the same time. Okay, so notice that now they're lined up. I push them, and in this case, I happen to push them exactly in the right way so that they actually lined up properly. Sometimes you'll get them one number off, and so that is an issue to deal with. In fact, I think here we're at one number off. But so the synchronization is an issue. if you need synchronization. In the project we're going to work on, we won't need synchronization. In other words, when the slave transmits and when the master transmits, the data is not as important in terms of how they're related, how the data is related to one another. It just needs to send that data, and so that's the issue. Well, this has been a good session. It hasn't actually been all that I wanted it to be. I was hoping to give an example of a little bit more substance, and so I've decided I'm going to create yet one more video on SPI communication, Arduino to Arduino SPI communication. So stay tuned for part C of this. Thanks for watching.